Mr. Klinkerman checking in with you with a little bit more from section 7.6. This has been a very packed section in which we're trying to see how do you use the first derivative and the second derivative in order to analyze the graph of a function. And what we're getting ready to do right now is we're getting ready to go with learning goal 4 for this section, which is that you are going to use the first and second derivative of a function along with other key features, vertical asymptotes, horizontal asymptotes, x and y intercepts, in order to be able to sketch the graph of a function. Alright, so this is a way where we don't have to plug in a ton of x and y values and so forth. We can use key features of a graph to be able to make its graph. It's a really cool process. Now the other thing that we still need to do, and this will be in the next video, the last video finally for this section, is we are going to look at the relationship between the graph of a function and the graphs of its first and second derivative, which is kind of a cool thing, and that's really it. It's kind of a cool thing. It shows that you understand some of the concepts behind the first and second derivative. Alright, but let's get back to where we're going to actually try to sketch the graphs of functions for today. And I want to talk with you a moment about what are the key features of a graph that you're going to need to use in order to be able to sketch the graph. Alright? And some of these things you can find using the equation of the function itself. Some of them you can find with the first derivative. Some of them you can find with the second derivative. Let's just go ahead and list them, and I'll point those things out on this graph as relevant. Alright, and the first key features of a graph that you're going to want to employ when you're trying to sketch a graph is you got to know where the x and y intercepts are. Now for this particular graph, those happen to coincide with one another because the point 0, 0 is both the x-intercept and the y-intercept. Okay, so along with the x-intercepts and the y-intercepts, another thing that you want to look for are vertical asymptotes and horizontal asymptotes. And you guys know basically how to find those, and you can see that this graph has a couple of vertical asymptotes. Looks like x equals, well, it's the square root of 5 and negative square root of 5 actually. And then you want to look for the horizontal asymptotes, which if you look at the equation of the function that I've given to you, you can tell that y equals 1 is a horizontal asymptote. Those are all important features of the graph. And those first 4 features are all things you can find using the function itself, not the derivative or the second derivative. Some other key features. Well, you want to find out where the stationary points of a graph are. I would say right now that you want to find where the critical values are, but critical values include vertical asymptotes, and we've already included those, but we want to find any place where the first derivative would be equal to 0. Anywhere you have a relative maximum or relative minimum value, in other words. And so for this graph, you can see one of those places right there. And after you've found the stationary points of a graph, you want to find out what are the intervals on which the graph is increasing and decreasing, and also where are any relative maximum or minimum values. Okay, now with this graph you can see that first branch is increasing the entire way, and then the first part of the next branch is increasing until you get to our stationary point, after which the graph changes to decreasing, and since it switched from increasing to decreasing at that stationary point, that made that a relative maximum value, and then the graph was decreasing the rest of the way. That's super important information when you're trying to sketch a graph. You got to know which way the graph is going and when it's going that way. And those last 3 things are all things you can learn from the first derivative. Alright, and then finally there are some things you can learn from the second derivative. We talked about how you can find the intervals where a graph is concave up or down, and how you can find out where the inflection points of a graph are. And for this graph, you can see that the intervals where it's concave up or down, well, here's 2 intervals where it's concave up. Here's an interval where the graph is concave down. It turns out that there was never a single point at which the concavity changed. It was at the asymptotes of the concavity change. In other words, there's no inflection points here. Nevertheless, all those features that you see right there are the important features of the graph of a function, and you have to be able to determine what those are if you're going to be able to sketch a graph just given the equation of a function. All right, now a quick summary there. Whenever you're trying to find these key features, you're going to use the original function f of x to find those first four things. You're going to use the first derivative of the function to find the stationary points, the intervals of increase and decrease, and the relative maximum and minimum values. Last part for now, at least. And you're going to use the second derivative to be able to figure out where the graph is concave up or down and where the concavity changes. In other words, the inflection points. Let's put this into practice. Now, I wrote the directions from exercises 7t right here because those are the directions I want you to be able to follow. Ignore where it says questions 1 to 4. Actually, for the exercise set itself, it's supposed to say 1 to 6 because the 6 problems there. But as far as we're concerned, we're just saying, for this example, let's sketch the graph of the function using the first and second derivatives to analyze key features of the graph, and we're also going to find any intercepts or asymptotes. Okay. Well, here's kind of the process I want you to go through when you're told to sketch a graph of a function. We know that we're going to be using the first and second derivative, and so it makes sense to begin by finding those two things. Let's do that. And this polynomial function is easy enough to do that for. Of course, the first derivative is going to give us f prime of x equals 12x cubed plus 12x squared. And then f double prime of x is going to equal 36x squared plus 24x. Okay, now the first thing we're going to go through are the features about the graph that we can find just from the original function itself. And those features, if you remember, were the intercepts and the asymptotes. All right, now remember, to find the x-intercepts, you have to set y equal to 0 and solve. So we would set 0 equal to 3x to the fourth plus 4x cubed. Then we can use a little factoring to solve that equation. We can say 0 is equal to x cubed times 3x plus 4. And then that's going to tell us that when x equals 0 and when x equals negative 4/3, you've got intercepts. And so the intercepts would be negative 4/3, comma 0, as well as 0, comma 0. All right, now to find the y-intercepts, you would of course plug in 0 for x. But if the graph touches 0, 0, that's both an x and a y-intercept, and it can only have one y-intercept, so we've got that covered. The other thing that you ought to be able to recognize quite easily with this one is that there are no asymptotes, because there's no restrictions on the value of x, and there's no limit, it turns out, on the value of y. All right, very simple one there. Next, we need to figure out determine the features that we can learn from the first derivative. Let's do that. And we start with trying to find the critical values. Now, we already know there's no asymptotes, but still we can find the stationary points, the points where the first derivative is equal to 0. And so we'll set f prime of x equal to 0, and we'll use factoring to solve that equation as well. We can factor at 12x squared out and make that 12x squared times x plus 1. And so we find that the critical values are going to occur at x equals 0 and x equals negative 1. And we'll see how you use those here in just a moment. And we're going to use the second derivative to try to figure out where are the possible points of inflection. And to know where the possible points of inflection are, you need to know where does the second derivative equal to 0. So we're going to set that equal to 0, and we're going to factor again. From 36x squared plus 24x, you can factor out a 12x. and that will leave you with 3x plus 2. And so the second derivative can equal 0 when x is equal to 0 or when x equals negative 2/3. Those are our possible points of inflection. Now we need to try to organize this information, and I'm going to try to help you do that. Okay, so let's start organizing. There, I've basically just restated all the information that we have already talked about. The last thing we need to do, well, not really the last thing, but before we can start drawing the graph, is we need to figure out which, if any, of the critical values are maximum and minimum values, and we need to figure out, does the concavity actually change at what we think are 2 points of inflection. And in order to do that, we've got to see when is the graph increasing and decreasing, and when is it concave down and concave up. And we're going to organize that on a number line, a pair of number lines. And what we're going to be doing on those number lines is examining when is the first derivative positive and negative, and when is the second derivative positive and negative. Now I'm going to be describing the process here and just writing the results down on the screen. I'm going to need you to confirm using your calculator or whatever tools you have that I'm giving you the right values. But let's look at the first derivative to begin. And if we want to know where the first derivative is equal to 0, well, we already know that's at negative 1 and 0. If we want to know where the first derivative is positive and negative, we need to check the three intervals created by those critical values. And so let's say we find out what f prime of negative 2 is. And it turns out that f prime of negative 2 is negative. And then between negative 1 and 0, let's say we plug in negative 1/2. F prime of negative 1/2, as it turns out, is positive. And then let's plug in, say, 1 for that last interval. And it turns out that f prime of 1 is still positive. Alright, now what did we learn from that? Well, the graph goes from decreasing to increasing at x equals negative 1, which means that we're going to have a minimum value when x equals negative 1. Now remember, to find out what the y-coordinate for that minimum value is, you have to plug in that number negative 1 into the original function. And if you plug in negative 1 into the original function, you're going to get that y is also negative 1. Now the second critical value is a little bit interesting because the graph does not change from increasing to decreasing or vice versa. It's increasing on one side of that value and it's increasing on the other side of that value, which means that basically we're going to have a scenario where the graph was going up and has a stationary point where the first derivative is 0, but then it continues up on the other side of that point. Okay, that's going to happen when x equals 0. Now for the second derivative, we're going to use the two values that we think are the points of inflection and see, does the concavity actually change as it gets to each of those points. Well, if you plug in any value less than negative 2/3, say negative 1, you're going to find out that the graph has a positive sign for the second derivative there. So it's concave up until x is equal to negative 2/3. Between negative 2/3 and 0, say at negative 1/2, you'll find that the second derivative is negative. So the concavity does change. And then for any value greater than 0, the second derivative is positive. And so the concavity again changes when x equals 0. So you have 2 points of inflection. Alright, we're going to have an inflection at negative 2/3. And then if you plug negative 2/3 into the original function, you'll get the y-coordinate for that point of inflection, which to three significant figures is negative 0.593. And you have a second point of concavity when x equals 0, and when x equals 0, y equals 0 also for this function, as we've already determined. Now let's translate that all into a graph. Just a word of warning, these lines are going to disappear from my screen, but you should have them written on your paper so that you can understand what I'm talking about as far as where the graph is increasing, decreasing, intercepts, all that kind of stuff. Alright, let's begin the graphing process here. And I want to remind you of all the things that we need to go ahead and include on the graph. What we would like to do first is we would like to go ahead and place the intercepts, asymptotes if they existed, as well as the stationary points and the points of inflection on the graph. And so I'm going to go ahead and put those things on there right now. Okay, now let's start with the intercepts. We said that there was an intercept at -4/3, comma 0. Alright, so -4/3, you can see the intervals that I made. That would be about right here. Graph is going to equal 0 there. And there's going to be another x-intercept at 0, 0. So let's graph 0, 0. We next want to go ahead and graph those maximum and minimum values that we found. Alright, now we found out that there was a minimum value at -1, -1. So let's go and graph that. There is a second stationary point at 0, 0, but of course we don't have to regraph that point, it's already there. Lastly, we want to graph any inflection points. And the inflection points, well, one of them was at -2/3, comma -0.6 essentially. So -2/3, -0.6, let's say that's right about here. And then we've already got 0, 0 graphed. Now look at the two number lines that we made that have the signs of the first and second derivative on them, and watch what I do with that information. We know that the first derivative is negative and that the second derivative is positive all the way up until x equals -1. So until we get to our minimum value, we know that the graph is decreasing and is concave up. So we can sketch that part of the graph right here. Alright, it's decreasing and concave up until we get to x equals -1. Alright, now notice I just went straight through the x-intercept. It was only an x-intercept and that was its only value. Now, once we get to -1, the first derivative changes from negative to positive, which means the graph is going to become increasing. And for the first little while, until x equals -2/3, the concavity is still up. So you can see that right here, now the graph is increasing and I've got it concave up. But once you reach the point where x is equal to -2/3, remember that the second derivative changed from positive to negative. And so we need to make our graph become concave down at this point. And watch how I do that. See how it's kind of opening downwards now? And that's going to go all the way until we reach the point 0, 0. Now once we get to 0, 0, which was an x-intercept, that was one of its purposes, but it was also a stationary point, and it was also a point of inflection. All right. The graph remains increasing, so we're still going to be increasing to the right side of that point, but the concavity changes back to positive. So right here, we're going to keep on going to the right, but we're going to change to concave up, and the graph is going to keep on increasing. There's the graph of our function f of x. Okay, now you're going to try a few of these on your own for practice. Concepts are simple enough, and I think you understand the process now of how you graph a function using the first and second derivative. Have fun.